Hi everyone, here we are for the second part of our chapter 17, which is we are looking at equilibrium. So we learned about the reaction quotient and equilibrium constant in the last part, right? Now we're going to look at the forms of K and Q. So let's say if it involves several reactions. Let's say for example, you want to find an overall reaction and there you can have 1, 2, 3, 4 like that. So let's say for the first reaction you have a certain Q. Let's say Q1, Q2, Q3 like that. Okay, so if you have overall, if you want to find out the overall Q, what you need to do is, so then you take these reaction quotients and you have to multiply then Q1 times Q2 times Q3 for the reaction quotient, and it would be the same thing for the K. K is the equilibrium constant. So if you have several reactions that involve that has different equilibrium constants, and if you want to find out what is the overall reaction equilibrium constant, you have to multiply them like this. Okay, so that's what it shows over here. And let's say if you have a, how can we relate your forward reaction with the QC for the reverse reaction? Let's say you have a reaction going A to B, and it is reversible. So if you write the QC, C means if it involves concentration. So for the QC forward, we're going to write concentration of B over concentration of A. That's how you would write QC for the forward reaction, correct? Now if you want to write the QC for the reverse reaction, let's say you want to write QC reverse. So for the reverse reaction, B going to be your reactant and A going to be your product. So you would write concentration of A over concentration of B, right? So QC forward reaction B over A, QC reverse reaction A over B. So B over A and A over B. Do you see that those are reciprocals of each other? For example, let's say QC reversible, right? So QC reversible, we define QC reversible is A over B. A over B. Right? So then that is, isn't that going to be the same thing if you take 1 over QC forward? So let's say you find out, you're going to go ahead and write down here 1 over QC forward, meaning B over A. B over A. Right? So this is A over B and this is B over A, meaning QC reversible equals 1 over QC forward. Right? Do you see the connection here? So QC reversible, which is QC reversible, A over B equals 1 over B over B over A, means that is the QC forward. So if you know the QC forward reaction, similarly QC forward would be equals 1 over QC reverse reaction. Okay, so they are reciprocal relationship. QC reversible equals 1 over KC forward. Similarly, if you want to make the connection with the K equilibrium constant for the reverse one would be equal to 1 over equilibrium constant forward reaction. Okay, we'll put this concept into a practice question and we'll try to understand a little bit more how we can use this in a question form. Okay, so another thing that we need to know, let's say you have a reaction and you are going to multiply that equation by a certain number. If you do that, so then your QC or the K also need to multiply by the same number. It's common factor. If the coefficients of a balanced equation are multiplied by a common factor, just like that, we have to multiply the concentration terms also by the same factor. Okay, q raised to the power 1 equals q raised to the power n. So this whole thing had to multiply by the same factor. Okay, so this is what it means. Let's say we have a reaction A plus B gives you C, and for when you are manipulating these equations, that you need to multiply. Let's say this has certain QC value, and then we need to multiply this whole equation by 3. So that would become 3A plus 3B giving you 3C. Okay, so then the QC is needed to be adjusted as QC raised to the power 3. Okay, so let's put this into practice with one example. We'll put all of these concepts in this one. Finding K for reactions multiplied by a common factor or reversed and for an overall reaction. A chemist wants to find Kc for the following reaction at 700 Kelvin. So this is going to be our target equation. 2 ammonia plus 3 iodine giving you 6 hydrogen iodide and nitrogen. We want to find out the Kc, meaning equilibrium constant, for this reaction. But you are given these two reactions. Use the following data at 700 Kelvin to find the unknown Kc. We are given one equation where nitrogen plus 3 hydrogen giving you 2 ammonia, and the Kc for that is given Kc1 0.343. Also we are given number 2, second equation, hydrogen plus iodine giving you 2Hi, 2 hydrogen iodide, and Kc for that reaction Kc2 equals 54. Now with these two we need to manipulate to get our target equation. Now what do you think we need to do with regard to the first one? Now we have to look at always our target equation. Nitrogen is a product. Here nitrogen is a reactant. Ammonia is a product here and ammonia is a reactant here. So what do we need to do this reaction? We need to reverse it, right? Reverse. We need to reverse this reaction. So our goal is when you add 1 and 2 after manipulating, we should get our target reaction. So if you reverse that, what's going to happen? There would be 2 ammonia. Number 1 is being reversed. 2 ammonia, reversible reaction giving you nitrogen plus 3 hydrogen. Now we are given the Kc for the forward reaction. So then what about the Kc for the reverse reaction? Kc1 reverse. Remember we learned in the previous slides, it's going to be 1 over Kc forward. So that means 1 over Kc1. So this 0.343. Okay. And then what about the second one? Now what do we need to do for the second one? Now let's see. For the second one, so here we have hydrogen. We reverse that, right? It's in this side now. Now hydrogen is a reactant here in the second equation. And our target equation, we don't have hydrogen. So our goal is to get rid of hydrogen when you add the two. Now in the first reaction, once we reverse, we have 3 hydrogen. So basically we need to make this also 3 hydrogen. So we have to multiply that by 3. Okay. And one more thing here, our target equation, we have 6 hydrogen iodide. Here we have 2 hydrogen iodide. So to get that to 6, we need to multiply this also by 3. So basically equation 2, we need to multiply by 3. 2 times 3. So the second equation multiply by 3, that would give you 2 times 6 hydrogen, 3H2 plus 3I2 giving you 6Hi and then the Kc. What happened to Kc if you multiply that equation by 3? Remember we talk about the Kc 54 now need to raise to the same power. 54 raised to the power 3. Now if you add these two together, we should get our target equation, which is the 2 ammonia plus 3 iodine giving you 6Hi plus N2. So 2 ammonia, where you add the reactants, 2 ammonia plus we have 3 hydrogens here, 3 hydrogens here. So they get cancelled. Okay. And then we have 3 iodine for the reactant side, 3I2. From the product side, we have nitrogen N2 plus 6Hi. Now, isn't it the same thing as this one now? 2 ammonia, 3 iodine, nitrogen plus 6Hi. Now we added 1 and 2 after manipulation. So what happened to Kc when you add Kc overall is going to be then K1 times K2. So basically this number that you're going to get, you have to multiply by this number. Okay. Now I showed you with my work here, but also the worked example is in the next few slides. So you can look at it here. We must manipulate reaction 1 and 2 so that they add together to give the target reaction. That's what we did. Reaction 1 must be reversed. You saw that. So the new equilibrium constant is a reciprocal of Kc1. When you reverse it, it becomes 1 over. And then reaction 2 must be multiplied by 3. You saw that too. So the new equilibrium constant is Kc2 need to raise to the third power. You saw that too. And we then add the two manipulated reactions and multiply their Kc values to obtain the overall Kc. So what we've been doing is what we discussed over here. Remember, if there are several K1, K2 or Q1, Q2, overall would be multiplication. K1 times K2. And then QC reversible equals 1 over KC or QC. Right? So the reciprocal. And also we're going to put this into practice too, since we multiply one of the equation by 3. So the Q or the K also need to raise to the power 3. Okay. So that's what I showed over here. Now it's also showing here the worked example. So we reverse this equation. Remember I showed you that the reversal of this. So then the K prime C1 going to be 1 over KC1, which is 0.343. So 1 over 0.343 is 2.92. And reaction 2 we multiplied by 3. Remember we multiplied by 3. So the KC2 also need to raise to the power 3. 54 raised to the power 3. Okay. Try this one. Kc2 is going to be 54 raised to the power 3 equals this value 1.6 into 10 to the fifth power. Let me write it down over here. 1.6 into 10 to the fifth power. It's not 105. That's a typo. Okay. It has to be 1.6 into 10 to the power. 10 to the fifth power. Do this in your calculator. Also see if you get the same answer. How do you get this number? 54 raised to the power 3. So you multiply 54 3 times. Okay. So by adding 1 and 2 together, you got the target equation like I explained. So then the overall Kc going to be the K1 C1 prime, which is this number 2.92 times K prime C2, which is K prime C2 1.6 raised to the power 10 to the 5. So this again raised to the power 10 to the 5. It's not 105. Okay. Raised to the power 10 to the 5. So do this calculation yourself and try to understand what we did. We reverse it, we multiplied it, we add the two together, and then the overall KC is again a multiplication. Okay, so we put everything that we talked about, how we can work with the QC and KC in this example. Okay, so the next one, the same thing that we talk about here in a summary form. Ways of expressing Q and calculating K. Let's say the form of a chemical equation, reference reaction going A to B. So this reference equation, Q reference, going to be, how do you find the Q? Concentration of B over concentration of A. And if there is a coefficient, the molar ratio, you then would take into consideration and you would raise that power here. Okay, so the value of K going to be, according to the reference equation, concentration of B at the equilibrium over the concentration of A at the equilibrium. Okay, and then if you reverse it, reference equation B to A, so then the Q is going to be 1 over Q reference. So this is the reference equation. Remember the reciprocal? So for this particular reaction, if you reverse it, Q going to be 1 over Q reference. Okay, so the Q equals 1 over Q reference. In other words, that's going to be concentration of A over B. Right? So the Q reference is going to be here B over A. So then when you move it, it will become A over B. Same thing here. K would be 1 over K reference, reciprocal. We talked about that. And if there is a reaction as a sum of the two steps, A goes to C and then from C goes to B. When you add these two together, you will get the overall reaction. So then the Q1, if you write the Q1 for this one, it's going to be C over A, correct? And Q2 going to be B over C. So Q1 times Q2. So you multiply these two, this Q1 times Q2. So when you multiply C over A, B over C, C to C get cancelled. Overall would be then B over A. Okay, overall reaction. So the Q overall going to be B over A, and in similarly K overall going to be, if you know the equilibrium constant for this one, equilibrium constant for this one, overall going to be, you multiply the two equilibrium constants, just like we had shown it in our example calculation 2. And if the coefficients multiplied by n, Q equals Q raised to the power the same coefficient that we multiplied, raised to the power n, just like 54 raised to the power 3 in our previous example. Same thing for the K, raised to the power n. Reaction with pure solid or liquid component, such as if you have a solid, then we do not put solid in our reaction quotient or equilibrium constant. Okay, so Q equals Q reference A equals concentration B, because this is going to be a solid. We don't put that. So the Q would be just the concentration of B, K would be just the concentration of B if A is a solid. So this is like summary of what we had talked so far. Okay. Now expressing equilibria with pressure terms, Kc and Kp. K for a reaction may be expressed using partial pressures of gaseous reactants instead of molarity. When you say Kc and Qc, that C means the concentration. Now K reaction quotient or the equilibrium constant can be expressed in terms of pressure. So then we call it as Qp or Kp. Okay. The partial pressure of each gas is directly proportional to its molarity. So we can use the same concept where, remember, Qc when we were expressing QC, we said concentration of the products over the concentration of reactants. So for this particular balanced equation, QC would be NO2 raised to the power 2, that's your products, over reactants NO raised to the power 2 and oxygen. This is the QC. And then the QP would be, we're gonna now replace the concentrations of these by the partial pressure. So since it is raised to the power 2, so then the partial pressure of the NO2 raised to the power 2, partial pressure of NO raised to the power 2, partial pressure of oxygen, it's just 1. Okay, just exchange concentration terms with the partial pressure. So we can express this equation Kp, meaning equilibrium constant for the pressure term, equals Kc. Kc is the equilibrium constant in terms of concentration. RT, R is here the universal gas constant, T is the temperature, and delta N is the change number of moles of change of number of moles of the gaseous molecules, only the gas. Okay, if the number of moles of gas does not change in the reaction, what happen? If delta N becomes 0, right, let's say the number of moles doesn't change, so then the RT, if delta N equals 0, RT raised to the power 0. Anything raised to the power 0 is what? Anything raised to the power 0 would be 1, right? So then if this term become 1, then your Kp equals Kc if the number of moles doesn't change for the gas. Okay, that's what it says over here. So this equation will be given to you, so you don't have to worry about how it came. Okay, let's look at this example. Ammonium hydrosulfide decomposed to ammonium and hydrogen sulfide gases. Find Kc for the decomposition. And we are given Kp. Okay, so we can use this equation. Kp equals KcRT delta N. Kp equals KcRT delta N. And this is the equation. Is it balanced? 1 nitrogen, 5 hydrogens, 1 sulfur. It's balanced. Kp is given to us. So we want to find out the Kc. Now, what is the delta N here? The difference in number of moles. Delta N. What's the number of moles of product? So this is gas, gas. So we have to look at the number of moles in terms of gases. So 1 ammonia, 1 H2S, 2 moles. And then ammonium sulfate, okay, over here this is a solid. So then the delta N going to be 2. Correct? Because there is no number of moles of reactants. So the products 2. So delta N is 2. So what we want to find out is Kc. So then the Kc would be Kp over RT raised to the power 2. Kp is given at 0.19. And the temperature, R is universal gas constant. I believe it's 8.313, or the other one now we're going to use 0.0821. So that's going to be 0.0821 is the gas constant. I will show it to you in the next slide also. And then what's the temperature? Temperature is 218. So what do you need to do? So we have to add 218 plus 273.15. Temperature we always need to convert it to Kelvin, which is 491. We can even omit 0.15 Kelvin. Okay, 491. So 0.0821 times times 491. See, this both product need to be raised to the power 2. So first you multiply these two and then raised to the power 2. So 0.19 over 0.0821 times 491 raised to the power 2 will give you the Kc. Okay. Yes, right here. Solution delta N 2 minus 0 2. Since there are two gaseous products and no gaseous reactants, convert temperature to Kelvin. We use this equation Kp, Kc, RT delta N. So the Kc going to be Kp over RT raised to the power delta N. Kp 0.19, your gas constant, times the temperature in Kelvin. You take the product of these two raised to the power 2 and you solve this, you will get this answer 1.2 into 10 to the raised to the negative 4. Okay, raised to the negative 4.